Hello, good afternoon, everybody. I hope all of you are having a great session and really enjoying and learning, interacting with all the experts and listening to them. Uh, I am Devarshi Das. I'm an assistant professor in the electrical engineering department at IIT Ropar, and I am going to be the session chair for this technical paper presentation session. So this is the session 2A in continuation with the session that we had on analog and mixed signals in the first half. In the first half, we looked at very interesting topics, the Cheetah framework, then the transmitter design for current mode continuous time linear equalization, and the linear dropout regulator in and a very advanced 7 nanometer technology. So keeping up with the momentum of that session, we will continue in this session and we have a good participation from industry as well as academic, and I hope you find this session equally exciting. So roughly what are the topics of this papers in this session are on temperature. The first presentation is on temperature sensor. The second one is on a technique for error minimization in continuous time sigma delta ADC modulator. And the final one is on a technique of on-chip jitter measurement in 65 nanometer technology. So with this, let us go into the first paper, which is going to be presented by Arpan Jain, and the title of the paper is a 180-degree phase shift biasing technique for realizing high CMRR, high PSRR in low power temperature sensor. So I would request to start the recording. And just before we do that, one point, audience, if you have questions, please feel free to put them in the chat box. I'll post those questions to the presenter at the end of the session.
Hello everyone, my name is Arpan Jain and I have completed my master's from IIIT Hyderabad. Today I'm going to present a biasing technique which is used to bias temperature sensors, and this technique will help you to achieve a very high PSRR compared to the previous techniques, and it will also require lesser efforts for the circuit design. So today I'm going to cover a brief introduction in which I'm going to discuss why we need the supply rejection in analog circuits. Then I will come to the temperature sensor architecture, what architecture we are using here. Then I will jump to this conventional supply rejection technique. I mean those techniques, previous techniques which they are which previously have been used to bias those temperature sensors. And then I will explain our proposed technique, how we are achieving the good PSRR, they're working, and then the comparison with the conventional techniques. Then I will explain the results, what results we are achieving, and finally I will conclude my presentation. So in introduction, we know in modern SoCs, we are embedding all the different blocks like analog blocks, digital blocks, RF blocks in a one single chip, right? And we know these high frequency blocks like RF circuits and digital circuits, they are switching rapidly and they are creating some disturbance on the power supply because they are taking a lot of currents, they are taking a lot of currents and currents is going up and down. Due to this, this power supply, it can't maintain the fixed voltage because of this switching and all. And this power supplies we are also providing to the analog blocks, and if our analog block doesn't reject those supply noise, this noise will come to the output of analog blocks, and which is not desirable, right? So that's why we need a good supply rejection in analog circuits. So all those noise can be filtered out, or these can be rejected from the analog blocks, right? So there are different methods to achieve the supply rejection in analog blocks. One of the very simple or basic method is using the cascoding. Cascoding is basically using the large land transistors, or basically the stacking series transistors. This will help to achieve a higher R0 and it will reject the supply. But the drawback is you need a higher headrooms. So for lower supply voltages, this technique is not very good. Okay, and another one is the LDO. In this LDO, we use an extra block which contains of an op amp and a voltage reference. It's kind of and they are connected into a feedback. So this block will help you to filter out or to reject the supply noise. But the problem is it will take a lot of area, basically because we are using the extra blocks and also the power. And again, the voltage reference required in this LDO is should also be designed such that it will automatically reject the supply noise. Okay. Another way is the feedback. By feedback, I mean basically we will design a circuit or a biasing circuit which will automatically reject the supply noise. They are connected into the feedback in a negative feedback. So it will automatically reject the supply noise. And this biasing we can use to bias other circuits. So basically that's what we are using here. That type of architecture we will use. So this supply insensitive biasing will use. There is a circuit which will automatically reject this noise. And those biasing nodes, basically the voltage or the current or for copying current, those nodes we will use to bias our temperature sensor and achieve a high PSRR. So now I will explain the temperature sensor architecture, what architecture we have used. So if you see this figure B, so this is a very basic architecture. This is also known as the composite pair, in which we have used the two NMOSes which are stacked onto the top, and then the gate is connected. Both the gates are connected to the voltage, same voltage. Okay. So this architecture has been has been proposed previously also, and this is a very well-known architecture. And what we have to do to achieve a highly linear p-type voltage, we have to bias, or we have to give the biasing current such that both the transistors should be in subthreshold region. So basically this I0 should be somewhat in nanoamps. So to make sure that these two transistors are in subthreshold region. So if we write the equation, you will direct and solve those equations. So you will get the p-type voltage, which is equal to KT by Q. Ln with the aspect ratios of the MCP1 and MCP2. Okay. So basically you will see the point is you will see this p-type voltage, this output voltage is highly linear with temperature. There is no process dependent parameter. So this is a first order equation. There are some approximations, but yeah, but you are able to achieve a very good linear p-type voltage if you bias those transistors in a subthreshold region. So there are many. So this technique, so this architecture is well known and previously used. So this same architecture we are using for our temperature sensor. So the previous techniques we can use PMOS to bias those transistors, or NMOS circuit, NMOS to bias those transistors. What we observe is NMOS, by biasing the current using the NMOS transistor, we are able to achieve a higher PSRR compared to PMOS. So that's why we choose the NMOS here. Okay. So the conventional supply rejection techniques, what they do is, so we like previously have said, there is a block which is required to which will bias this NMOS, which will make sure the current in this circuit should be nanoamps, so that the MCP1 and MCP2 will be in subthreshold, and they can give a good linear p-type voltage, which can be used as a temperature sensor. So the biasing circuit, so what previous or conventional techniques are doing, so if the supply voltage increases, so what they do is they're biasing this NMOS. So let's say there is a PSRR, there is a supply rejection of this circuit. So if VDD increases, there will be small increment in V bias. Let's say, taking an example, the supply rejection ratio of this circuit is 60 dB. So let's say if there is a 1 millivolt increase in supply, so then the V bias will increase by 1 microvolt. So this although this is a very small increment in V bias and it is rejecting the supply by 60 dB, but you will see if there is a small 1 microvolt increment in this, so the gate to source voltage will also change by very small value, right? So this effect, because this is a small change, the small current will also increase. So this will also have a proportional effect on VP-TET, and you see you have certain limitations. So you by increasing this voltage, this VP-TET will also increase by a very small amount, right? So, but previous techniques are using this type of biasing, in which the VDD increases, the V bias will increase by a very small amount, but it will increase. So that's why we are calling also the previous techniques, we are calling it a 0 degree phase shift. Okay. So here to explain it more, what we are trying to say is, let's plotted the x-axis, the PSRR of V bias, basically the where this output node V bias which we are achieving, and on y-axis I'm plotting the final output of the temperature sensors, PSRR, basically PSRR of the temperature sensor, which is this VP. So if you observe here, so you see there is while increasing the PSRR of V bias, when the maximum PSRR achievable at the output of temperature sensor is 80 dB. And to achieve the maximum PSRR, we need to design somewhat near around 120 dB. We need to design the supply independent bias voltage such that it will reject the supply. Its PSRR should be near to 120 dB. So we can achieve the maximum PSRR at the output of temperature sensor, which is VP. So let's say if we don't want to go to 120 dB, let's say 70 or 80 dB is good enough for PSRR or V bias. So we can get somewhat near 70 dB. But the problem is, again, designing the 70, 80 dB PSRR for this supply independent voltage bias circuit is quite difficult. To achieve a 70, 80 dB PSRR, or also considering all the PVT variations, it's quite difficult to achieve in low power supply voltages. So here comes our observation. What we observe it, what if we use the same circuit, same biasing, but if we can if this supply voltage increases and we are able to decrease the voltage of the biasing by a very small amount. And the reason is because what we are trying to compensate is, if you see if VGS, basically VDD increases, the VDS of this M0 will increase. But if this V bias decreases, so VGS of this M0 will decrease. So what we're trying to compensate is, if the supply increases and the increment in VDS, because there is a R0, right, in this transistor. So so there is an increment in current. By this small increment in current, if we decrease using the VGS, so we can exactly cancel out this effect, right? We can cancel out the effect of supply on the current, and this VP dat can remain constant. So this is our first idea, or the first observation we did. And you also, by question, you can see if VDD increases, if there is a possible circuit which will decrease the biasing, that is VGS decreases, and at the same time, because VDD increasing, VDS is increasing. So if this both VGS decrease and VDS increase, we can compensate. So we can still achieve a very good PSRR supply rejection ratio. Okay. So what we did is, we simply again simulated the same graph. On x-axis, this is the supply independent biasing PSRR. On the y-axis, it's the final output PSRR. So you see, like we said, right? If so, at somewhat near around at 40 dB PSRR of the supply independent bias, this is V bias, we are able to achieve almost very high PSRR, right? You can see some more. It's a simulation based. So we said that there is a one block which a 180 degree phase shift biasing technique, and which is saying VDD increases, then there is a small decrement in V bias, and as we thought, this is able to compensate this, and you see we are able to achieve the maximum PSRR. But the problem is, this is kind of a pin on a stone. We can't say that we can achieve this 40 dB, exact 40 dB PSRR for all the chips. We know there are a lot of variations. We know there are a lot of PVT variations in the circuit, and we can't say we can simply get 40 dB in every chip, right? So, but the point here is, why we don't also need to bias our circuit at 40 dB. What if we bias somewhat little higher than this, let's say some 50 dB or 55 dB. So we choose somewhat near 55 dB here of the PSRR of this circuit, and let's say there is a change in this 55 dB PSRR due to PVT variation. Still, we are able to achieve a maximum PSRR of this, right? You see, there is a maximum PSRR you're still able to achieve of 80 dB. While in the previous, if we go in the previous circuit, you see there is to achieve the maximum PSRR, you require a very high PSRR for the biasing circuit. But here, you don't need that. Circuit design constraints are very less. You don't need a very high PSRR. By simply getting a lower PSRR also, you are able to achieve a very high PSRR at the output of temperature sensor. And so that is what our technique helps to from the previous or the conventional technique. So here are the results. So if you see, this is in left hand side, this is the PSRR of our supply independent biasing. So this here, you see there is a 180 degree phase shift we are able to achieve, and this is the And this is basically we designed such that it should able to achieve somewhat near a typical the value of -50 dB. And this on the right hand side, I'm showing the results of the PSRR of the VPTET, basically the output of our temperature sensor. So here you can see with the process variations, with all the process variations, FF, SS, and other variations, our output PSRR is changing from -80 dB to -79 dB, which is good thing, right? This is the Monte Carlo simulations, which shows the reliability of our technique. So we are running for the 1,000 samples, and which include the process and mismatch. So we are on the x-axis. I am plotting the PSRR of this of the output of the temperature sensor. So you see this PSRR is hardly changing, and it is changing from -180 dB to 79 dB. So which shows the reliability of our circuit. That means if we bias our temperature sensor at 55 dB, we can achieve the maximum PSR of 80 dB, and it is not changing, right? So this will actually reduce the constraint on circuit designing, and at the same time we are able to achieve the maximum PSR using this 180-degree phase shift technique. So so this explains now we have the previous results are the PSRR, which is at basically 1.8 volt supply, but now we have run the supply variations from 1 volt to 2.5. You can see at different temperatures. This temperatures or the output of temperature sensor is quite constant. That shows how good it can reject the supply. And on the right hand side, I'm showing the temperature sensor output with temperature. So basically the VPTET voltage with the temperature, you can see how good linear they are and how effective with the process they are also. So this is the composite pair. So this concludes my presentation. Basically, I present a technique, a 180-degree biasing technique, which we call, which helps to achieve the high PSRR. This will also eliminate the designing efforts which we previously required for the supply-independent biasing circuit, which requires a very high supply, which require a very high supply rejection ratio to achieve a higher supply rejection ratio at the temperature sensor. So yeah, that's it from my side. These are some references. Thank you.
Hello. Thanks, Arpan. Do you hear me?
Yeah.
Thanks for the great presentation.
Yeah,
it was really an interesting work. I would request the audience to put questions till the time they do so. I have a couple of quick questions, Arpan.
Sure.
In your paper, you have said that no extra circuit is needed to generate V bias, but you are using indeed some circuit which generates a 180-degree out of phase signal. So why do you claim it to be so that no extra circuit is needed?
By no extra circuit, we mean like we don't mean because we need one biasing, right, to bias our transistors. So by extra circuit, we mean like we are not using an LDO or op-amp extra to make the circuit feedback. Whatever previous biasing techniques are there, so the circuit which we are using, it is already proposed and have been used in many circuits. The main observation is we can compensate, we can get a good high supply rejection with the same circuits or without using extra hardware or extra more circuits, like I said, op-amps and all. So for that, I mean like that. But
Okay.
one biasing circuit is required, right? We have to bias something, so we need one biasing circuit.
Okay. Coming to the next point, slide 9. The circuit, you would need a startup circuit, right? Have you considered it in your design?
Yes, it's already there. Just we didn't, because we only want to convey the technique. I mean, it's more kind of a technique compared to the circuits, because most of the circuits is already used. This temperature sensor is already used and all, but only the observation. So that's why we didn't include the this thing startup circuit. But definitely we have to use a startup circuit.
Yeah. Again on slide 9, so you show that at a particular value of V bias PSRR, there is a peak of the V PTT PSRR, right? Okay. So what is the intuition behind that behavior? Like what causes that peaking of the PSRR?
Yeah, so that's what like at that point basically it is the maximum cancellation of VGS and VDS. So like I said, we know in an NMOS transistor there is a R naught. Let's say supply is changing, the supply is at the drain terminal of NMOS. Okay, so there is a VDS, there is a drain resistance which I'm saying R naught, so which will cause some increase in current. Okay, and at the same time we are using a 180-degree phase shift, so VGS is decreasing some very small amount, but it is. So this peaking is at that point which is exactly cancelling whatever, if there is a supply rejection which is exactly cancelling this VGS with VDS. So you will see no change in current, right? There is no change in current, and the PSRR or the rejection will be the maximum at that point. So
Yeah.
only at that point you will see some peaking. So it's a simulation based. We simulate it at every values and see where it is peaking like that.
Yeah. Okay. I'm still awaiting questions from audience, please. Okay. I'll have the last quick question. Again, it's on slide 10, where you have shown the plot of PSRR versus frequency. And the PSRR is high only till about a few kilohertz, if I remember well.
Right.
But
It's totally.
yeah, and in the paper also you have written about immunity against high frequency switching things. So, but high frequency switching is anticipated to be around hundreds of megahertz, if not more. But at those high frequencies, the PSRR actually drops. So, how do you plan to extend this work to take care of high frequency switching?
I mean, for high frequency switching, one basic thing, because here we didn't add any RC circuit, one way is to add some RC circuit. I mean, to reject those things, but because problem in this temperature sensor is it's biased with a nanoamp current. Actually, it's in biased in a sub threshold to achieve a linear p-type voltage. And in our application, we are targeting also for I mean, not very for high frequency, it's for low. But yeah, there is one limitation I can say here. I mean, in this, at least in this, because we are biasing very low currents here, and with nanoamps current, it's quite difficult to achieve. I mean, such a high PSRRs or rejection things. So I
Yeah,
mean, we
so
can.
got it. Yeah, so it's basically the speed power trade-off that's kicking in. That's what you're trying to come at. Yeah.
Right.
So I have one question from the audience. Why is PSRR limited to 80 dB, not reaching 120 dB? What are the bias voltages generated for different supplies with your circuit? What are the bias voltages generated for different supplies by your circuit? So two questions.
I mean, I didn't. First question. I mean, I am not sure. I understand completely. Can you repeat again?
Yeah, why is PSRR limited to 80 dB?
So this PSRR, they are talking about the, because there are two circuits. We are talking about the PSRR of two circuits. One is the biasing, and another one is the final output result PSRR of the temperature sensor.
Mm-hmm.
So for I mean, so again, it depends on the circuit design. The temperature sensors. So if I take the example, let's take the final temperature sensor, which is limited to 80 dB. So again, you can increase the PSRR by increasing the lengths of the NMOS using a very large lens in the NMOS, but hardly it will help you. I think it's a limitation to the circuit design, or I can say because the R naught is limited, right? We can't achieve very high R naught. It's limited to circuit. So it depend on circuit how much PSRR we can achieve from that.
Okay. Thanks, Arpan. In the interest of time, I'll not take any further questions, but definitely you can interact with Arpan. I request the audience to interact with him and post him questions, any further questions directly to him. So let us, thanks. I'll first thank Arpan for joining in and for the presentation. We'll now move to the next paper. So the next paper is about real-time multi-bit DAC mismatch estimation and correction technique for wideband continuous time sigma delta modulator. And the 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 lead author of this work is Ankur Bal. Ankur, are you there? Yes.
Yes, yes.
Yeah. So let us have the presentation. I would request the audience again to post their questions in their chat box. Okay, let us have the presentation.
Hello everyone. Today I'm going to make a presentation on a paper titled Real-Time Multi-Bit DAC Mismatch Estimation and Correction Technique for Wideband Continuous Time Sigma Delta Modulators. So I'm Ankur Bal, who's going to make this presentation, and my co-authors are Sharad and Rupesh, and all of us are from STMicroelectronics India. So the agenda of my presentation is as follows. I'm going to talk about oversample data conversion and the merits of using sigma delta conversion, especially continuous time sigma delta modulators. And we'll talk about the impairments in the feedback DAC and how to get around those impairments. I'll discuss few techniques, contemporary techniques. Then I'll talk about our proposed technique for tracking the DAC mismatch errors, estimating them, and eventually correcting the DAC mismatch impact at the modulator output. And finally, I'll present results and conclusion remarks. So when we talk about oversampled analog to data conversion, we first just take a look at a Nyquist straight sigma delta converter, where the ADC is operating at Fs and we have the quantization noise that is spread between 0 to Fs by 2. So increase the precision, of course, this is going to come down further, and the higher the precision, lower the quantization noise. And another way of getting it down is to increase the sample rate of the ADC, and as you can see here, we've increased the sample rate k times. We see the quantization noise coming down, and we can in fact theoretically keep on increasing the oversampling rate to get a much better in-band performance, and use a digital filter to get rid of the outer band noise. But again, this is going to be limited by the ADC linearity, the linearity basically of the ADC components, and also the thermal noise. Sigma delta is an attractive proposition because what happens by using a sigma delta modulator is that it gets rid of the quantization noise for a given oversampling ratio to a band that is out of the band of interest. So here you see this is the out of band region, and it has pushed the quantization noise in band to out of band. So it has kind of high passed it. That's why sigma delta modulators are very popular in being deployed to make high performance ADCs. Again, you have a low pass filter to get rid of the out of band noise, followed by a decimation to reduce the rate of the output. Before I touch upon continuous time sigma delta modulator, just a snapshot of a discrete time modulator here. So we have an anti-aliasing filter at the input of a discrete time modulator, which comprises a sampler and the complete modulator implemented in discrete time. So it of course shapes the quantization noise out of band, but there is a possibility of foldback if the if the out of band tones or noise or interferers are not filtered out by the anti-aliasing filter, because this is going to alias anything that, beyond the half the sample rate. So this is a very important part, and anti-aliasing filter. So we talk about continuous time modulators. The sampler is moved after the loop filter, just before the quantizer. This results in the low pass filtering action by the loop filter itself. So we have the input subject to a low pass filter, and then the sampling is occurring just before the quantizer, and this in fact circumvents the need of an anti-aliasing filter. That's one of the big advantages, because the loop itself is acting like a low pass filter here, so we don't have any fallback here because of the sampler. And secondly, it's a continuous time system, not a discrete time, so you don't have any clocks and switching happening, so it's more power efficient also. That's why the continuous time sigma delta modulator is an attractive candidate. Just mentioned that sigma delta modulation will obtain good signal to noise ratios by oversampling and subsequent noise shaping. As you can see here, it's going to shape all the quantization noise out of band, and this is basically done by the loop. And here the model of the quantizer, we have quantization error being injected into the quantizer. It's being modeled like that, and we see that the noise transfer function, or the transfer function that the quantization error is subject to, quantization noise is subject to, is 1 upon 1 plus Hs. Hs is the low pass loop filter, so this is a high pass transfer function, and this is the digital output, n bit wide, and usually these are unary codes, so we have a segmented sorry, not segmented, we have a unary DAC elements here. So for example, for a 4-bit DAC you'll have 15 DAC elements, and in a non-ideal world there's going to be some kind of a mismatch here between them, and this is being modeled as an EDAC, and we'll see that it results in the reduction in output of the modulator performance. So there are going to be some spurs, in-band spurs, because of this mismatch. So we'll see how to mitigate the mismatch. So one of the techniques is the data weighted averaging technique. So this is the modulator, quantizer, the output going to the DAC. So the DAC here is modeled as the ideal DAC plus a non-ideal one. And when we talk about first order DWA, it is barrel shifting in digital, and it basically high passes the DAC mismatch error. So the one minus Z inverse is the high pass transfer function. And if you're implementing the first order DWA, we do get reduction in the DAC error that is being injected into the loop. And in case you want to use it at much higher frequencies, because as the modulator frequency increases, you need to do the DW also at a much higher frequency. So, and also the quantizer also needs to run at that frequency. So in order to achieve that, time interleaving has also been proposed. So you have a time interleaved output with DWA performed and injected to a high speed DAC in the feedback loop. But then again, it has its host of issues, and just put it for the sake of reference here. And another method to overcome the DAC mismatch is to estimate it and get rid of it in the data path itself. So we have the gray, the analog in the gray, the dark gray, the light gray is the digital, and the white is also the digital part. So these are the DAC, analog DAC elements. For example, if you have a 4-bit DAC, you want to have 15 of them, but here it is proposed in this particular paper, it is proposed that we have an additional element, and all these elements are going to replace this path, this element in this particular path in round robin fashion, and the element here is going to be subject to a pseudo random noise that is going to be injected here and pass through the signal transfer function and the quantizer, the complete modulator transfer function, and eventually it is going to be estimated by a correlation function. So we have this error which is going to go through TTF, which is going to mirror the journey of the signal through this particular path. So it is estimated here, this transfer function, and CT is basically a digital equivalent of the GT, and that is used to basically estimate the the magnitude of the DAC elements, and it is plugged into here. So one by one each of them is estimated, and the error transfer function is modeled here of the DAC, of the modulator, sorry, and the output of the DAC is subject to the error transfer function, and it is subtracted from the data path at the output of the modulator. So in this way, the this particular method gets rid of the mismatch error in real time in background by injecting a signal. So what two things to note here: you have a signal injected here, and this part is the estimation part is running at full rate. Estimation and correction is all running at full rate. So we thought, can we do something so as to first of all get rid of an external alien signal being injected, any pseudo random. Suppose we don't want to inject that. And secondly, can we do it at a reduced rate, the estimation and correction? So what we did was we modeled the analog DAC that is there in the feedback loop in digital. And how we did that, we had an estimator, which I'll briefly describe in my next slides, which basically estimated the DAC elements and modeled it and plugged it here basically into the DAC digital model. And why we did this is because we see that at the output of the DAC, the mismatch is high passed by the loop itself. For example, here it's a third order loop. It's high passed by 1 minus E inverse cube. But unfortunately, this is an analog node. So somehow I'm able to get a digital equivalent node here. Then I'm going to high pass the mismatch of that. I'm going to get an output which will high pass the mismatch of the DAC. So as you can see here, it is the input plus the high passed quantization noise plus the DAC mismatch error. So this is a basic model of the DAC, of the unary DAC. So I write it thermometer because the quantizer output is a thermometer code, but this can be as any unary code output. So we have again for a 4-bit DAC we would have had 15 elements here, and driven by these digital codes BIs and BJs here, and we see that of course the summation of the unary codes that are driving these current sources is not zero. So we basically define an entity NIK such that NIK is given by this expression, and the summation of NIK is 0. This is needed for the correlation function to work. So we need, because here BIK is not bounded, it is going to change. The summation of BIK would have changed every signal iteration, every iteration of the loop. But here we define an entity such that the summation is 0. And we work out the so actual here is basically the output of the DAC. So the DAC output is BIK, summation of BIK. So delta here is again the quantization step, and for a non-ideal DAC you have the BIKs plus the error. So you have a 1 plus EI, 1 plus minus EI associated with each and every DAC element. The DAC error. And if you work out the algebra, we can actually show that it is just summation of BIK plus NIK multiplied by the error, where summation of NIK we defined was 0. So if you look at the modulator output, it is the signal transfer function. And of course, the input subject to the signal transfer function, the quantization noise subject to the noise transfer function, plus the summation of the NIKs multiplied by the error and the error transfer function here. So this point. So this is what this output is. So we have STF, NTF, and this part, these three things here. So what we do is we have an output here, and we recreate, we basically recreate this path in digital. I'll just show you in the next slide how we do that. And we do a cross correlation between the NIK here, because the BIK is going inside the DAC, the unary DACs. So we generate a NIK here, and we emulate this path, and we do a cross correlation function, and we see that by using a high pass filter we get rid of this, we get rid of the signal here, so this becomes 0. The cross correlation between the quantization noise and this is also 0, and this is the only term that is left, and we use this to estimate the DAC mismatch error of its elements. This is how the whole thing actually looks like. So the white again is the analog part, this is the digital. So we have the scrambler, here that scrambles the unary codes so as to decorrelate the subsequent, the consecutive outputs of the DAC. So there is a scrambling that is happening here, and we have the NI case being created here. We pass it through the error transfer function and the high pass filter again to get rid of the signal, the first term that I mentioned. We have a correlation that is running to, the thing to note here is it's running at a lower rate, decimate by n, and we do a correlation of each and every element one by one in round robin fashion, and we continuously update the DAC memory, and as I showed you at the output of the DAC memory we will have the DAC mismatch error high passed. So this is how we do. So this is the estimator plugging in the coefficients into the DAC memory. So these are some of the results. This is the pre-correction. We switch off the estimator and the corrector. With the plus minus 2% DAC mismatch, it looks something like this. A lot of spurs here. THD is bad, SNR is bad. And just zoom into the post-correction results. We see that the THD has increased manifold, and the other performance figures will also increase. So these are actual simulation results. So I'll conclude by saying that we have actually demonstrated a 50 dB improvement in THD for a 2% DAC mismatch, and we don't need any extra alien signal or pseudo random code to be injected into the system for estimating and correcting. It's a background process, but we don't need to do anything. So we with an extra signal going in, and it happens at a reduced rate. I showed you a decimate by n, so you can actually decimate it by quite a bit. Only thing is the penalty is it takes time for it to converge, but I guess it's good enough for many applications. And as I said, we do it in a round robin fashion, single source at a time, so we don't have to concurrently compute the errors. So that also results in further hardware savings. But another thing that needs to be taken care is a dynamic mismatch. We are just talking about static mismatches. So at higher frequencies, this could also pose a problem, which also will need to be addressed along with the static one, which we have already shown. So thank you. Thank you for your attention, and any questions are most welcome.
Okay, thank you, Ankur, for the presentation.
Thank you.
Yeah. So I request the audience once again to post their questions till the time they post. I have a couple of quick questions. So the first one is with respect to the plot that you have shown in the paper about error correction with percentage change in DAC error. So as the percentage error in DAC goes up to 5%, we see that the SNDR, instead of keeping on reducing, slightly picks. It's 112 dB. So, why is this phenomenon being observed? Can you throw some light on that?
So I think you're referring to the paper, right?
Yes.
Okay.
So that's the main result, I guess, in this work.
So it's more of a simulation result, and I would say it is. I don't think there would be a significant change, right? Is it a significant peak?
It's a 6 dB rise.
Okay, so maybe at the moment I am not able to exactly recall what you are exactly referring to. Maybe Sharad can pitch in just in case but at the end of the day, these are different mismatches that we had modeled from the actual SPICE models, So the mismatches that we get, we plug it into the MATLAB model, and we try to get the result. So I'm just wondering that whether it is a statistical anomaly, because I don't recall any such pattern that you, yeah.
Okay, so the next question is the technique that you have proposed is based out of mathematical models and also use some SPICE models. So what sort of CMOS technology related non-idealities do you expect to become challenges when you go ahead with this technique on silicon? So keeping in mind especially the low technology nodes. So
Right. So that is a very good point you make. The technique that we present is basically for removing static mismatches. In fact, in my concluding slide, I touch upon the point that when we are talking about something working at probably much higher frequencies, that time probably there would be, because of DAC switching, there would be much more noise that would be injected, and that could also pose an issue. So here what we are talking about in this paper is purely for static mismatches, and here the results that we demonstrate are basically for 28 nanometer technology. And when you go into smaller nodes, but if you keep on increasing the frequency, as the frequencies will increase, the challenge of dynamic mismatch will actually I would say become more dominant. So if you're working at lower oversampling ratios, probably not going beyond maybe 2 gig, for example, 2 gigahertz, because up to 2 gigahertz we do have some techniques, right, that can actually compensate for dynamic mismatch. But if you're going for a much wider band ADC with much higher frequencies, then of course static mismatch is not the only thing that you need to look at.
Yeah. Thanks for the clarification, Ankur.
Yeah.
I'm yet to receive any question from the audience. Okay, then let me go ahead with the last question. Then, what are the trade-offs in this technique that you have proposed? Is the robustness against static variation that you are gaining out of this technique? What is the price you are paying for that?
Okay, so the first price that we are paying is in terms of time. Of course, our biggest assumption is that these parameters aren't changing with time, and of course they are changing, but at a very slow rate. Because one of our claim in this paper is that we are running the whole system at a much lower rate. So when you are running something at a lower rate, then you are taking much more time to do that estimation, because the correlation function needs millions of samples before it can actually converge on a single value, and we are estimating each single current source one by one. So it has to go through, for example, if I talk about a 4-bit DAC, it has to go through 15 such cycles, and that too something that is running at a decimated rate. So the trade-off here, I would say, is the time. So say in a scenario where probably you have temperature or voltage, something that is varying the DAC mismatch, the static mismatch over at a higher rate, so there it could be an issue. So the main trade-off here is the time, but again we gain in the power.
Yeah. Okay. Thanks, Ankur.
Thanks.
I have one question from the audience, so and I'll make this as the last question. Any specific reason for plus minus 2% DAC mismatch?
No specific reason. In fact, there was from the present DAC, like in our one of our projects, we did calculate the sigma, right, for the current source variation, and from that the worst that we could come up with for that particular specification was plus minus 2%. And of course, I would say that theoretically you can actually, as you mentioned in our paper, we have shown up to 5%. But at the end of the day, there would be other things that would limit. It is not like in the MATLAB simulation, you see the floor going down to minus 130, minus 140. But there would be non-linearities, there would be thermal noise, right? There would be other things that would limit the performance. So this number came from a real case, I would say, project case.
Okay. Thanks.
Thank you
for the presentation and for the answering the questions.
Thank you, Devarshi.
Thanks. Okay, so we'll move to the next paper, and perhaps this is the last work to be presented in this session. And this work is a 10 gigabits per second on-chip jitter measurement circuit based on transition region scanning method. And this work will be presented by Santunu Sarangi. Santanu, are you there?
Yes, I'm here.
Yeah, hi Shantanu.
Yeah.
Okay. So let us start the presentation.
So good morning, all of you. So this is Santunu Sarangi. So I'm a research scholar in IIT Kharagpur. So my supervisor is Professor T.K. Bhattacharyya. So today I'm going to present a conference paper. So the topic name is 10 Gbps on-chip jitter measurement circuit based on transition region scanning method. So as the name suggests, so we have designed a on-chip jitter measurement circuit which will measure the peak-to-peak jitter of a 10 Gbps SRD transmitter stage. And as its name suggests, that transition region scanning method we are using, where we are scanning the transition region of the data or clock. So from that we are measuring the on-chip jitter. So this is the outline of this presentation. So first introduction, we'll give some introduction about the jitter, then background. So on-chip jitter measurement background we'll discuss, then problem statement. And we'll discuss the proposed work and simulation results. And we also fabricated a chip, so we'll show you the chip implementation. And final and also we'll do the test setup and measurement results also. And finally, we'll give the comparison results and conclusion. So this is the introduction of the jitter. So as you can see, that jitter is basically if the transition means the point it deviates from its ideal points for data and clock. So the jitter will form. So the two examples I have given, the data jitter and clock jitter. So here the peak-to-peak jitter. So basically the top one is the eye diagram of the data signal. So where it's a peak-to-peak jitter is showing, and the bottom one is the rising edge of the clock. So here it's a peak-to-peak jitter. So basically jitter generated from the parasitic effects and the skin effect and dielectric losses in the medium, and also some oscillator phase noise, power supply noise, and PVD variations. So basically the as the jitter creates some undesired effects in the system performance, so we have to measure. So basically off-chip measurement is there, on-chip jet measurement is there. So off-chip measurement is straightforward. So for that costly instruments are used, and also for that chip we need some high frequency pin, and also need some on-chip high performance drivers to drive the equipments, and there are limited number of pins you can access, and sometimes if you directly measure the jitter from the die, so costly probe stations are required. So that's why the off-chip jitter measurement is not preferred. Sometimes the off-chip jitter will not give the correct result. That's why on-chip jitter measurement is one of the best method, because inside the chip we'll measure the jitter and will convert to some other form, and we'll easily check or measure at the output of the chip. So this is the background of on-chip jitter measurement procedure. So there are several on-chip jitter measurement methods are there. Previously, researchers have already worked on this type of. So basically, this EOM method, ACS, asynchronous clock sampling, TDC methods, PD methods. So it has individual advantages and disadvantages. Basically, the TDC method is most popular. It's simple design and most digital circuits are used, but the resolution is very less. So for that, analog methods are used, but it's complex and some power consumption is more, but the resolution is good. So, but these all have some limitations. So these are the limitations we have found in the previous research work. So not all OCGM circuits are able to measure both data and clock jitter, and some are used reference clock, though the reference clock is not pure. So basically, finally they are measuring the relative jitter, and in the swap reference clock, only clock and period jitter measurement is possible, not peak-to-peak jitter. And timing resolution also is limited, means it's not measure the very minimum timing, means jitter. And also TDC-based OCGM circuits use off-chip processing, which is means reduces the performance. That means it reduces the speed of the operation. And this is the proposed work. So here we are using the OCGM circuit for peak-to-peak jitter measurement, on-chip jitter measurement. For that, we are using a novel transition region scanning-based method. So it's completely new, and it's a lot of features are there in this particular method. So basically, first we will measure the peak-to-peak jitter measurement for this scan TRS-based method. And it's extremely good timing resolution, means jitter as minimum as jitter measurement is possible, means minimum jitter we can measure. And dynamic range also very good. That means you can measure up to 0.9 UI, means unit interval. And complete analog design and on-chip solution. That means no off-chip processing, so speed is high. And also measurement of both data and clock. So we are measuring both data signal and clock signal. And we are using sub-rate clock in the reference case. So though it's sub-rate, that means some multiple of the data signal or clock signal. So the power consumption and the circuit complexity is less. So this is the system where you are using on-chip jitter measurement unit. So in this system, this is a transmitter system of Sharad system. So here the one part is that is data generation circuit, the second part is clock generation circuit, that is the PLL, and third part is the jitter generation circuit. So here to measure, to validate our circuit, we need some jittery data, that means peak-to-peak jittery data. So for that we have designed this all the circuits, and finally we are giving that jitter data to our on-chip jitter measurement unit to measure the peak-to-peak jitter. So this is the conceptual diagram of the complete TRS-based OCGM circuit. So here means the first three blocks, pulse width generator, phase shifter, and transition region detector, is one circuit, that is transition detector circuit. So here the pulse width generator generates a pulse. So based on the input data and its delayed version. And that pulse width will be fixed. That is means that is the offset time that is fixed. So if any jitter will be added in the input data, then pulse will be shifted its position, but the pulse would be same. So that will give to the transition region detector, and simultaneously will give a shifted clock. Okay, so we are using some VCTRL control signal, and also we are giving a sub-rate clock. So that output clock is shifting. So that output clock, shifted clock, is basically scanning that pulse width, and after the scanning, finally it's giving the output jitter value. So this output jitter is in a timing format. So we are not directly measuring this. So we are converting again to voltage, and finally we are measuring the voltage in terms of, means we are measuring the jitter in terms of voltage. So this is the circuit in the block diagrams of the complete circuit. So one is the transition detector, another is to voltage converter. The transition detector we have discussed, that is pulse width generator, then phase shifter, then transition means that transition region detector. So three circuits are there inside the transition detector, and this jitter to voltage converter basically uses a constant current source and time to voltage converter circuit and a peak detector. So which is finally convert to that peak-to-peak jitter to peak-to-peak voltage. So this is the complete implementation of the OCGM circuit. So this part is the pulse generator. Basically, it's taking the data and its delayed version and giving to the XOR gate. It's giving a pulse width. So that pulse width is fixed some time, offset time. And if any jitter is added, that pulse will be vary from left to right. So that is scanned by a shifted clock. That shifted clock is generated by the VCTL circuit. So we are giving a control voltage to the digital circuit. So based on that control voltage, so that clock is shifting. So that is current. So this will give the output of that means total pulse width, amplified pulse width, which is nothing but the jitter peak to peak, plus some offset. What is the pulse width? That value, that jittery value plus that pulse width. So total value will get here, and some supporting blocks are there. So once the jitter will be over, then what happens is the output pulse should be down to 0, but we'll wait for some time. We'll wait if any jitter will be there or not. So for that, we have arranged this type of circuits. Basically, it's counter circuits. So we'll wait for some time by using some count, so that once there is no jitter, then it will be the jitter output will be 0. Then finally, that amount of time is nothing but peak to peak jitter. So this is the result of that circuit. So here we are control voltage, we are increasing, we are ramping. Then this 34 nanosecond is nothing but that pulse width after the pulse generator. So whatever that is 34 nanosecond, that is fixed. So this is we can say the offset jitter. So and the 6 nanometer we are in the third plot. So that is waiting time, because we are waiting for some time, checking whether any other jitters are there or not. So now this is the plot. So this is the offset. That means at the 0 picosecond input peak to peak jitter. So 40 picosecond we are getting. So actually it's 40 nanosecond because we said that it's amplified version of that jitter, because we are using the control voltage such a way that so it is amplifying 1000 times. That means if the jitter is picosecond, then we'll get 1 nanosecond at the output. So it will be easy for our measurement. So here for 0 picosecond jitter, the TD output is 40 nanosecond, that is offset. So once after this, if any jitter is added at the input, so linearly the output will vary. So this is the simulation result for the output. And this is the phase shifter we are using. So basically to shift the clock, that means sub-rate clock. So we are using 4 stages we have used, because for a 10 Gbps the maximum jitter as we are assuming is 100 picosecond. So for that we need a delay of delta delay of 100 picosecond. For that we are using 4 stages. So here the result is for 1 stage. So that is worst case, it's 40 seconds. So it is sufficient to measure 100 picosecond. And this is the jitter to voltage converter. Basically, TVC circuits used and a peak detector and unit gain buffer is used to convert the jitter to voltage. And this is the result. This is for different jitter cases, how the TVC output means is changing, and also the peak detector output. So this is the peak TVC output. This is the peak one. So the peak detector is detecting the peak value, and it's stay in that point. Again, when it's peak, then it's detect and stay. So in this way, we are getting the outputs. So finally, this is the jitter peak to versus peak to peak voltage. So it's for different TVC gain. This is useful because for measurement, if the gain of the TVC is more, then it will be easy for us to measure in a higher resolution. And this is the chip implementation. You can see this is the chip micrograph, and this is the complete layout. And this part is OCGM circuit. So this is 910 micrometer, and this is 300 micrometer. And this is fabricated in 65 nanometer technology. And this is the test setup. So you are using different equipments, and this is our PCB, and this is one socket. Inside that socket, our chip is there. So we are measuring our outputs. And this is the final measured output. So this is jitter peak to peak input jitter peak to peak, and this is the jitter peak to peak voltage. So millivolts. So you can see it's almost means following the predicted value, whatever value we have predicted, that is value. Means there is little bit deviations are there. but it's a good match to that predicted value. So you can see, and up to 50 picosecond we have measured. So based on that we are giving the giving its milliwatt. So it's actually calibrated. So based on this value, we can get means that this voltage is calibrated with the peak-to-peak jitter. So once we measure the voltage, so we can actually calculate it, the peak-to-peak jitter. So this is the comparison result. So we have compared several previous research work. So the TDC methods and asynchronous clock sampling methods and analog or PD methods and EOM methods we have done. So by comparing the previous, this work is TRS method. So we are using 10 GPS data and clock, 10 GPS data or 5 GHz clock for measuring the jitter. And the resolution is, we are getting very good resolution, that is less than 1 picosecond. And the processing is completely on chip. That means nothing is off chip. So almost all components, everything is inside the chips we are measuring. And auto calibration is added. So here in this circuit we have not shown that, but it's actually added in the complete circuit. So we are using also reference clock, but that is sub-rate clocks. It's a sub multiple of data. So that reduces the power consumption and the complexity. And we are using, finally the power consumption is 11.4 milliwatt, but some components we have not shown here. So that's why it's 10.4 milliwatt. And this is the area we are using to 73,000 micrometer square. And we are using the process technology is 65 nanometer. And here the power consumption, the clockwise power consumption we have shown here. So the TD circuits transition detector that contains all the means, and that pulse width generator, then BCDL circuits plus that transition region detector. All this is completely taken 65% of power, and other circuits also that BCDL 24% and calibration unit 7%. And this is the conclusion, successfully measured the peak-to-peak jitter and achieved good timing resolution, less than 1 picosecond, very good dynamic range also. I'm fabricated in 65 nanometer with silicon area up to 73,000 micrometer square, and the power consumption is 11.4 milliwatt. These are the references we have used. Okay, thank you.
Hi, Santunu. Thanks for the presentation. It was really very interesting. And I have many questions from the audience. So this time, let me start with the questions from the audience. So the first question is how to avoid temperature impact during jitter measurement. Have you considered it in your
basically we have designed that calibration, cursor calibration circuit. So that circuit completely is responsible for any static and dynamic errors. Whether it's a PBT errors, so there's a temperature variations, anything that will take care.
Okay. So moving to the next question, could you explain why non-linearity in the delay versus voltage curve doesn't appear? Are you doing some calibration for that?
Basically, we are using that current star based delay line. So that's why that non-linearity will come. So, but that will doesn't matter because we are measuring the peak-to-peak jitter. So whatever the non-linearity will come. So finally, the peak-to-peak jitter we are measuring. So that will not affect. Means whether it's that the BCDL non-linearity will be there. Still, it will not problem because ultimately we are measuring the peak-to-peak jitter. So that's the thing.
Okay. Moving to the next question. In the proposed design, will the circuit only measure relative jitter between subsampled clock and the input data?
No, it's completely purely it's measure the data and also it's purely measure the clock. So for that, we are giving a sub multiple of that's external clock. So that will scan the data or clock, it's transition region. So that will not any correlation between that the data or clock with this sub-multiple clock. So it's purely measure the actual jitter. It's not measure the relative jitter like other.
Okay. It seems to be a follow-up question. It is that won't the jitter of the clock going to the phase shifter affect the measurement? Won't the jitter of the clock going to the phase shifter affect the measurement?
The same thing I said, means though you are measuring the peak to peak, so I don't think that even if that non-linearity part or anything will come to that phase shifter, so that will affect, because finally means that shifted clock will cover all the transition regions. Okay, whether it's a non-linear or linear, but it will cover. Okay, maybe it will fast in between, means at the center point. Suppose the control voltage will be the middle of this voltage. So that time the phase shifter will shift the clock fast, but ultimately it will measure all these things. So that also we have another control, that means if we reduce the control voltage generator's gain, then we can solve that problem also.
Okay.
Indranil, you would like to add something? Yeah, hi. Yeah, so actually it is basically the peak-to-peak jitter measurement technique. So suppose there is a non-zero value of the clock jitter. Of course, it could have, it is possible. So now the situation is that basically it is measuring the jitter with respect to, it is basically tracing the jitter from one time to another time in the time domain. Now, if there is a, let's say, delta t amount of the clock jitter is there, and you have the data jitter of delta t1, so worst case value will be delta t plus delta t1 in the sense. But that offset delta t1, as Santunu is trying to say, that the delta t1 offset will be a constant offset which can be subtracted from the original measured value. And the delta t1, as there is no direct correlation between delta t and delta t1, the data jitter and clock jitter, that offset will be a static offset rather than it will be the dynamic offset. So in the measurement, in the course of measurement process, if you subtract that peak value or peak jitter of the clock, then you can originally, you will get the, on the average, you will get the peak to peak jitter of the data or any of the arbitrary signal you will take. So the question, whatever the audience is asking, I understand that whether it will affect the static jitter measurement or dynamic jitter measurement. It will not have any direct effect on the dynamic offset, rather than it will have a static offset which can be easily subtracted.
Thanks, Indranil, for the clarifications. I have one question. The jitter to voltage converter circuit that you have shown has one capacitor, right? So there is no discharge mechanism as shown in it. So I was just wondering, how do you discharge that capacitor?
Maybe in that figure, not means that one transistor is there. So sometimes it will reset to discharge all this, but maybe it's wrong. Means I have not drawn that transistor, but there is a path. Yes.
Okay.
Yes.
Okay. So thanks for all the answers to the questions from audience and also my questions. I think with that, in the interest of time, I have to close the session. So thank you all for joining. Thanks.
Thank you.
Thank you.